Coming. So this week we finally have Dabeen Lee coming back to IBS. He was our first member of Discrete math group, and now he's a professor at KAIST. And we will talk about ideal things, right? Clutters and ideals.
Yes.
Yeah, please.
Thanks very much for the invitation and your kind introduction. It's always great to be back here. I used to be here for 3 years as a postdoc, and then I left last year. And it's been over just 1 year at KAIST. And now teaching something continuous, not discrete. But I always like working on combinatorial optimization, and this is out of my PhD thesis, but we ended up submitting this paper like 2 months ago. So I thought that this might be the perfect place to announce the result and advertise about it. So I guess this is some small area, but it used to be a very important area in combinatorial optimization. But I guess we are kind of losing people. I guess like strong people are retiring these days. So I guess if anyone is interested in this area, I guess feel free to contact me. And I guess Ahmad is also working very hard on this topic. So okay. I think maybe some of you are not familiar with this area, so I try to make this as a gentle introduction to the problem. So I guess the first 80% of the talk will review the existing works, and I organize those things as a motivation for my problem. And for the last 20%, I'll just quickly go over my results with Ahmad. Okay, so the conjectures that I'm going to talk about are motivated by perfect graph, which is more famous, I guess, in the literature. And also, there's a nice theorem about characterizing the structures of perfect graph. But I'm not going to talk about the strong perfect graph theorem by Seymour and others, but I'm going to talk about the original perfect graph theorem by Galois. I mentioned that, and that was a motivation for something called replication conjecture, which is the set covering analog of the theorem. And then I'll quickly go over set covering problems and what I call clutters, and talk and define max flow in cut property. If you're familiar with polyhedral combinatorics, it's related to what's called the total dual integrality. Okay. And then the last part is about my work with Ahmad on tackling some of these conjectures. Okay. Great. So a graph is perfect if for every induced subgraph, its clique number is equal to chromatic number. Okay. So by definition, if a graph is perfect, then every induced subgraph is also perfect. It's a minor closed property.
Induced subgraph.
In the subgraph, yes. Right. Oh, sorry. I'm gonna get to a minor operation in terms of clutters, so don't get confused with my terminology. So every time I say minor, it will be something about clutter minor, which could be different from your language. Anyways, so the perfect graph theorem is due to Galois, and it says the following. So if a graph is perfect, then its complement is also perfect. And what is the complement? Well, you look at each edge, and if there's an edge in this original graph, then the complement there's no edge, and vice versa. Okay. I heard that many people at the time were working on this theorem, but they couldn't. Well, I guess Galois used to be a grad student at the time, but he figured out the solution for the theorem. And the way he proved is based on something called this replication lemma. Okay, and what is the replication? Okay, so you are given a graph and you take a vertex of it. Okay, the replication operation is the following. So you first add a copy of this vertex, and then you add an edge between every neighbor of the original one and its copy, and then you are adding an edge between the original one and the copy. So this is the replication operation. And Lovász proved that if a graph is perfect, then if you take its replication, it's also perfect. Okay. And we know that every induced subgraph of a perfect graph is also perfect, and taking this replication is perfect. We can combine these two statements. So for any non-negative integer weights, you construct another graph with it. So if there's a weight, if there's a vertex with weight 0, then you just delete it. If there's a vertex with strictly positive weight, then you replicate the vertex w minus 1 times. Okay. Then you can easily argue that the resulting graph is also perfect. Okay. Just sequentially delete vertices and replicate vertices. Okay, I'm gonna get to this statement later on, but let me review this definition and the big perfect graph theorem. Okay. We can combine these two statements to give an equivalent definition of perfect graphs. So if you take a graph and its complement, then this statement holds. So the clique number of the complement is equal to the independence number, because clique becomes an independent set in the complement. And the chromatic number of the complement, which is the minimum number of disjoint stable sets to cover all the vertices. And stable sets become cliques in the complement. So the chromatic number becomes the clique cover number, which is the minimum number of cliques to cover all vertices, disjoint cliques. So using this observation, we can redefine perfect graphs. So if a graph is perfect if for every induced subgraph, its independence number is equal to clique cover number. I guess in combinatorial optimization literature, I guess talking about independence number is more common. That's theory. That was the reason why I talked about this redefinition. Okay, so I want to restate this condition that independence number equals clique cover number in terms of optimization language. Okay, so getting this independence number and clique cover number themselves are some optimization problems. Okay, so any induced subgraph is represented by some vertex subset, and a vertex subset itself is represented by some 0, 1 vector like this. Okay. Then the independence number can be computed by solving this little integer program. Here M is the clique vertex incident matrix, so the rows correspond to cliques and columns correspond to vertices. Okay, and so you're allowed to take at most one vertex from each clique. That's basically a stable set. Okay, and this computes the weight, but W is 0, 1 vector. If some component of it is set to 0, then there's no reason to select it, because you're not increasing the objective. But if you choose that one, then it actually restricts your choice of choosing stable set. So if some weight is set to 0, I guess you better just not take it. So this optimization basically computes the independence number. Okay. And here, this minimization problem is so the C is the family of cliques in this graph. Okay. Written in this, it's written in the rows of this matrix M. So you are choosing some sets of the cliques to cover vertices with respect to this weight. If this WV is set to 1, you need to cover this vertex. If this weight is set to 0, then you don't have to do anything. I guess let me just move on. I guess this is not really important, but I guess I'm just saying that the independence number and clique cover number can be written as these optimization problems. Then you can say that a graph is perfect if these two optimization problems are equal. Okay, and we often say that this is a min-max relationship. And in fact, if you are familiar with linear programming, if you forget about these integrality conditions, this thing is the dual to the original problem.
And you want to replace with a non-negative?
Right. You replace this by non-negativity. For linear programming, we know that the duality always holds, but we are taking this integer point. So this relationship does not always hold. But if this thing holds for every 0 1 vector, then the underlying graph is perfect. Okay. Any question?
There any epsilon net type theorem here. Sufficient condition guaranteeing the integer solution is bounded by a function of the rational solution.
You mean for this problem?
Yes.
I'm not aware of such a result. Maybe there exists one. Okay. But anyways, if this thing is true, then you can define perfect. I mean, if you're interested, there's something called like theta body, which is a semi-definite program, and okay, there's some results going on about comparing this integer linear program and robust theta body. And if your graph is perfect, then the theta body is equivalent to this integer program. There's something going on in terms of optimization, but I'm not aware of precise statement you asked for. Any other question? Okay, so suppose that my graph is perfect, saying this min-max relationship holds true, and the graph is perfect. Remember this statement. So if you take any non-negative integer weight and replicate your graph according to this vector, and this weight vector, and then you get this resulting graph GW, and this one is also perfect. Using the definition of in the previous slide, we know that this independence number and the clique cover number are equal. Okay. And in fact, the independence number of this resulting graph can be represented by the same optimization problem. But here W can be arbitrary integer vector, not just 0 1 vector. And the clique cover number is defined as this minimization problem. Now you can take any non-negative integer vector instead of 0 1, because here W can be an arbitrary non-negative integer. Okay, so again, as this independence number and the clique number are the same, we get this min-max relationship, but this is true for every non-negative integer vector. So all we just obtained is that if you start with a perfect graph, meaning this min-max relationship holds for every 0, 1 weights, we just argue that in fact this statement holds for any non-negative integer weight. Okay. So in the previous slide, we assumed this statement, which is equivalent to say that the graph is perfect, and we use this statement using the robust replication lemma, and we argue that the min-max relationship holds for any non-negative integer. Okay. And I just summarize what we just argued in the previous slide. And this thing is true. Question? Okay. We talked about like graphs, perfect graphs, and here used to be the click vertex instead of matrix of a graph. But in fact, we can take any arbitrary zero matrix M. It doesn't have to be this click instead of matrix of a graph. You can take any zero matrix, and the same statement is also true. Okay. This is not a difficult result. Basically, that the important case where this thing holds is basically the click matrix of a perfect graph. If you are not given a click matrix for M, then this statement doesn't hold for every one. Okay. Right, and here, when you take an arbitrary zero matrix, the corresponding family C will be the vertex subsets represented by the rows of this matrix. And in that case, this problem on the left-hand side is just a general set packing problem. Set packing in theoretical computer science can mean like something different, which is in the dual side of this problem. But in combinatorial optimization, we call this problem as set packing. It's like you're packing vertices in your graph, which you turn into tables. Okay, and the replication conjecture is the set covering analog of the previous statement. Okay, now you're taking some zero matrix M. Okay, and again the rows are labeled by this family C. This C captures the vertex subsets represented by the rows, and the columns correspond to the elements. And if you look at this left-hand side, it used to be a maximization problem, and also this inequality was less than or equal to. But the objective became minimization, and the inequality direction was reversed. Okay? And this is the covering problem. So you're taking at most one vertex in each subset. Like in a click, you're taking at most one vertex. But in this problem, for every subset, you have to take at least one vertex. This is covering vertex. Now you are taking the minimum weight cover. Okay. And again, the dual on the right-hand side, now it has maximization instead of minimization. And the inequality used to be at least W, but now it's at most W. Okay. So the statement says that if this is true for every 0, 1, now we have to consider plus infinity weight. Then it holds for every non-negative integer. Surprisingly, this conjecture is still unsolved. It seems to be much more complicated and difficult than the previous statement. There are like much more complicated classes of structures understanding this question. Again, basically the class of graphs or combinatorial objects satisfying this min-max relationship is essentially the perfect graphs. But it seems that the classes of objects satisfying this condition are much more diverse. Okay. That's why maybe that's the reason why it's hard to understand this conjecture. Question? Yeah.
Is there an example which shows why you need the plus infinity?
Plus infinity?
In the I suppose this conjecture is false if you don't have the plus infinity there.
I think so. So if you set, so the reason why we have this plus infinity is that you are setting, if you have plus infinity, now I have like minimization problem. I'm setting the vertex to be 0. Right? Because I mean, if you set that part to be 1, then
Okay. So
I guess, right? So in the previous case, when you have weight 0, then you set vertex to 0. But in the minimization part, you're taking plus infinity.
I see. Yeah.
For some vertex.
This is to make it feasible in a sense, or is it feasible?
I guess you have to kind of consider the operation of deleting some element, and that's yeah.
So yeah, right. So this lets you sort of encode and use subgraphs in a different way.
Right.
Ah,
I mean, right. So in the previous case, we had only 2 choices, and now we have 3 choices. But I guess it looks artificial. But I guess in terms of like minor operations and deleting operation and contraction, and I guess that this seems natural.
Yeah.
Right. Any other question? Okay. And this is called replication conjecture because you can restate the same statement as combinatorially, and the resulting combinatorial interpretation is similar to this is analogous to replication lemma for packing problems. Okay, but I'm not gonna talk about it. Okay. So the left-hand side, just to kind of give you some terminologies, the left-hand side basically computes some set of elements which intersect every subset in your family, and combinatorial optimization community calls it a cover, but the TCS people call them a heating set or transversal. Okay, it's on the left-hand side. We call it the set covering problem, but TCS people call it heating set problem. Okay, the second part. So somehow like we are trying to prove some similar statement as the set packing problem. So for the set covering version, we try to translate this result for set packing in the world of set covering. So let me get into basics of set covering problems. Okay, we used to use notation V as in vertices, but I guess it's more common to use edges or elements in the set covering version. Let me just change to E instead of V, just so that you get, when you read papers, I guess you're not getting confused. So C is a family of subsets of the elements. They are called members. And Edmonds and Fulkerson define what's called a clutter. In the literal sense, like elements are clutters in a messy way. And the definition is basically something is a clutter if every member, no member is contained another one. There's no hierarchy in this family. For example, when you have these 6 elements, when you can take these 3 sets, there's no inclusion relationship satisfied, so this is a clutter. And in graphs, you take 2 distinct vertices S and T. Now you're including all ST paths. That's a clutter. Okay. Also, you can collect all spanning trees. That also gives you a clutter. And the blocker is basically a collection of covers, right? So we talked about set covering problem, which is to compute minimum weight fitting set or minimum weight cover, and when you collect this blocker is related to that concept. So again, I'm given a clutter, and a subset of the elements is a cover if it intersects every member in the clutter. Okay, and the blocker collects all minimal covers. Okay, if something is covered, then you can kind of start eliminating elements until it's not a cover anymore. Then you get to minimal. You get to a minimal cover. When you take the blocker of the clutter of ST paths, then you get the clutter of minimal ST cuts. Also, if you take the blocker of the spanning trees, then you get minimal cut. Okay, good. And it's known that if you take the blocker of the blocker, then then you get the original one. Okay. Why do you care about this? Well, I guess there's a nice example of network interdiction games. So there are two players, and one player tries to connect two distinct locations by kind of setting edges. The second player tries to disconnect these two locations by deleting edges, and then you kind of repeat this sequentially. Right, so one player tries to recover some member of the original clutter, and the second player wants to get a member or get a cover from the block. So, like now, then you can ask like, what is the minimum size of a cover? Okay. So that's basically the combinatorial optimization comes in this domain. So this tau of C denotes the minimum size of a cover, which is called the covering number. And this here nu of C denotes the maximum number of disjoint members. Okay, so there are some disjoint members, and we have to intersect every member in this disjoint set. And you have to take at least one element from each of these disjoint members. And that implies that covering number is always as large as the packing number. Okay. And in general, this inequality is strict. This is one small example. So this is a K4, and now you're taking the clutter of triangles in K4. That's called Q6. Okay, there are 6 edges, and each triangle has 3 elements. This is the incident matrix, member element incident matrix of this clutter. There are 6 elements. There are 4 triangles. The covering number is 2. You need at least 2 elements to delete all triangles in K4. But the packing number is 1 because there are no 2 disjoint triangles in K4. Okay. So one question that's studied a lot in the literature is this question. We know that the covering number is lower bounded by the packing number, but can you upper bound the covering number as a function of the packing number? Can you find some polynomial function f for the upper bound? That's one question that's studied a lot in the computer science. But our question is asking for some exact statement. So when is it that these two numbers are equal? We know that this relationship is strict in general, but can we study the case when these two numbers are equal? And we say that a given clutter packs if these two numbers are the same. Okay. And there are many nice examples, like so if you take the clutter of ST paths, then the covering number is the minimum size of an ST cut, and the packing number is the maximum number of disjoint ST path in terms of edges. And then we know that the Mangal's theorem implies that they are the same. And this is less famous than the Mangal's theorem, but there's a theorem by Lucchesi and Younger saying that the minimum size of a dijoint is equal to the maximum number of disjoint dipoints. Okay, so then the question is like, but the question asking when a given clutter packs is not well defined. Let me give you an explanation. So in fact, if you can take any arbitrary clutters, but you can embed that into a larger clutter that actually packs. Okay. So let's look at this example. So these two clutters C1 and C2 are something very complex and arbitrary, but I'm adding two more elements. Okay. One element appears every member from the first one, and the second element appears in every member of the second clutter. This one, the covering number is 2. You can select this element and this element. The first element covers all members from the first family. And the second element covers all members from the second family. And packing number is 2. You can select one row from the first set and one row from the second. Okay. So, but what's happening over here and here could be arbitrary. Okay, we can embed any structure inside this clutter that packs. Okay, so how can you avoid this construction? Well, I guess that's the motivation for studying the clutter minor operation. Okay. So we're gonna define two clutter minor operations. So they are contraction and deletion. Contraction means you delete this element, okay? This element from all members containing it, but then some members might become non-minimal, might contain some smaller member. Then you just remove them. Okay?
Remove the smaller member.
Remove that member that contains a smaller one. You're just taking the minimal subset after removing these elements. Okay. But deletion operation, you remove this element. You also remove all members containing this element. So if you delete this one, you're gonna discard all the first rows. Okay. And a clutter minor is what's obtained after applying these operations sequentially. And in this example, if you can delete the second element, then you're gonna discard these rows, and you contract the first element, then you get C1. And you can do the same for to obtain C2. Okay. So you can hide and embed some complex structure inside this clutter. So, right. So, with this minor definition, we know that this clutter packs, but there are minors of it that do not pack. So, better question is the following. So, when does a clutter satisfy that every minor of it packs? And if that's the case, we say that the clutter has the packing property. We're asking whether every minor, not just the clutter itself, but also all minors of it, all proper minors of it. Okay. This is by definition is a minor closed property. Okay. So if a clutter has this property, then all its proper minors also have that property. So if a clutter, so the question is basically, can you find a minor of a clutter that does not pack? Okay. If something does not pack, then can we kind of dive more into its minors until every minor of this packs. And the last moment when you stop, before you stop, is for this minimally non-packing. So it does not pack, but every proper minor of it packs. Question? Okay, so if the clutter does not have the packing property, then all its proper, it has a minimally non-packing minor by definition. Okay, what properties do these clutters have? By using the same famous celebrated Lehmann theorem about characterizing minimally non-ideal clutters, I didn't define what this being ideal means, but a clutter has the packing property that we can say that it is ideal. I haven't defined what it is, but I'm gonna do it. But this is also a minor close property. We'll define it later. But if a clutter is ideal, then every minor of it is also. You can also define minimally non-ideal clutter because it's a minor close property. Using this theorem, we can say this following statement. So every minimally non-packing ideal is ideal or minimally non-ideal. Why is that? Because it's minimally non-packing. Every proper minor has the packing property, and it is ideal. Okay. So if this is non-ideal, then it is minimally non-ideal. That's it's nothing but just kind of the simple logic. Right. So this theorem and this one relies on these famous like structural characterizations of minimally non-ideal clutters, and this, I mean, you just look at its structures to deduce this statement. But so minimally non-ideal clutters have been studied a lot, but ideal and minimally non-packing clutters are relatively less studied. Okay. Until this paper, and they kind of in this paper, these three people started talking about started investigating ideal and minimally non-packing clutters, and one of the conjectures that they are thinking is true is something called the tau equals 2 conjecture, meaning if a clutter is ideal and minimally non-packing, its covering number is always equal to 2. Okay. Well, this looks too simple to be true, but until today, we have like hundreds and thousands of examples. All of it have covering number 2. We don't have a counterexample until today. Okay. I don't know the answer. I guess some part of, I guess like 50% of my PhD thesis was to find a counterexample to this conjecture, but I failed. So if you are interested, you can, I guess IBS has this supercomputing facility. You can write a code for open this. Well, it's important because it's related to the replication conjecture that we talked about at the beginning. Okay, it says that if this thing is true, then we can prove that the replication conjecture also is true. If you solve this, then question.
Yes. Finish what you want to say. Okay.
Well, I mean, this is just all I wanted to say.
Do you know if there's a half-integral version of these types of conjectures?
Replication conjecture.
Yes, for example, if I just add 1/2 in
Wow. That's a very good question. There exists like fractional version of some other statement or idealness, but not for this packing and packing property. But you can, I guess there's no reason not to kind of consider it as stable, right? People, and including myself, have studied the like fractional version of this state, some other statement, but I don't think like people have studied the kind of fractional version of half integral version of this. Any other question? Okay, so let's get into the max flow in cut property. Okay, it's basically an extension of the covering and packing. The covering and packing are talking about the size of sets, okay, like binary weight 0 or 1. Or we are extending that thing to the more general weights. So again, the covering number and packing number are defined by this optimization problems with unit weights. But we can consider weighted packing and weighted covering. So for the minimization problem, we can assign arbitrary weights, and for the packing, instead of bounding the number of times we can pack is 1. We can choose an element multiple times with these weights. Okay. And this is the weighted covering number, and this is weighted packing number. And again, on Clutter text, if the weighted covering number and weighted packing number are equal for unit weights. And Seymour introduced this notion of max flow in cut property. I guess as the name suggests, the clutter of ST paths which lead to maximum flow. I mean, if you remember the max flow in cut theorem, it says that maximum value of a flow is equal to the minimum size of a ST cut. And that actually holds for any weight. And this definition is motivated by that example. Anyways, so what about the packing property? So we have defined this minor operations, contractions and deletions. We can redefine this operation in terms of optimization terminologies. So in terms of packing and covering programs and numbers, contracting means setting the weight to a large number, so that we do not pick this element. And deleting is equivalent to setting the weight to 0, so that we are always taking this element. Okay. We have already taken this element, so we don't have to consider other members that are containing this element. That's the same as kind of removing or ignoring the members containing this element. But if you do not pick this element, then you have to still consider like the other elements in members. Okay, and so basically this minor operation or the covering number of a minor can be defined by introducing some weights, like 0, 1, plus infinity weight. Okay. Right, so we can redefine the packing property. Again, the packing property was that every minor of this clutter packs, and that condition can be restated in terms of this weighted packing and covering number for all 0, 1 plus infinity weights. Again, if this was non-negative integer, then the property was called the max flow in cut property. And by definition, max flow in cut property is more restricted. But this is if your clutter has this max flow in cut property, then it has the packing property. Okay. Question? Okay. So examples of ST paths and dijoins. The clutter of STPs and the clutter of dijoins have the max flow with cut property. Okay. One more definition. Sorry about this. We talked about this idealness. Okay. Idealness is about fractional version, and I talked about some other statement that I was looking at in terms of half integrality. This is related to this ideal clutters. So fractional packing and covering numbers can be defined in terms of these optimization problems without the integrality condition. Okay. And you say that clutter is ideal, then some equality relationship holds for some fractional numbers. And I do care about this because it's related to integer programming. So a clutter is ideal. Then you can look at this polyhedron defined by non-negativity and this covering constraints. Okay, this is a polyhedron. If a clutter is ideal, if and only if this polyhedron is integral, meaning all its extreme points are integral in our integer vectors. And we do care about that in integer programming. If you optimize a linear function over this polyhedron, then you always get an integer solution automatically. Okay. Right. So this is a nice picture. Like looking at the classes of clutters. So idealness is the largest one, and inside there's this packing property, and by definition max flow and cut property is more restricted than the packing property. And in fact the replication conjecture states that these two classes actually coincide. They have to be collapsed. Yeah.
Does this mean that whenever you have the idealness property, you have a polynomial time algorithm for the optimization problem?
Well, I guess it depends. Depends on the size of your input.
Yeah.
I guess sometimes if you're given this matrix M, then right, if that's part of your input, then it's polynomial time. But often, like maybe if you think about spanning trees, then the number of rows in this matrix will be the number of spanning trees.
Does not necessarily imply that the separation problem is
Right.
But don't you just need some subroutine which generate
Right.
the first constraint?
Right. So whether or not you can separate this violated inequality depends on your combinatorial structure. Like if you think about cliques, there are exponentially many cliques, and separating on a row for a clique is not polynomially solvable, I think. It's not always well, okay.
But for perfect graphs, it is because it's the same problem.
Right. Any other question? I guess you are almost getting towards the end. So. Great. And again, this is a tau equals 2 conjecture. In the same paper, they proved that this conjecture implies the other one. Okay. So we were motivated by the replication conjecture, and one way to answer this is to tackle this tau equals 2 conjecture, which seems to be simple, but somehow like this implies this one. Okay, so for the last 10 minutes, I'm gonna state one way of trying to attack these conjectures. Okay, that's out of my contributions. Okay, so answering this replication conjecture would be nice because it's analogous to the replication lemma for perfect graphs. Okay. As one conjecture, tau equals 2 conjecture implies this conjecture, can you try to answer this? Or, on the other hand, this statement seems to be simple. So can we try to find counter example? Well, I guess what you need to do is to construct a clutter that is ideal and have covering number at least 3. And surprisingly, constructing such a class of clutters is difficult. That's what we found. Okay, and then I guess one natural way of constructing clutters of covering number at least 3 is what follows. So I'm gonna consider what's called the multipartite clutters. Okay, so you look at, it's like if you remember like multipartite math, bipartite graph and tripartite graph and so forth. This is basically that. So your graph, there are like disjoint sets of elements, and when you have a member, you're allowed to take one element from each part. Okay. Then
So not necessarily on the same row, right? You just pick one from each.
one from each. Yes. Yeah. So each member intersects every part precisely once. Okay. And by definition, these EIs, these parts, each of these parts will be a cover for this clutter. Okay. And so basically, you can increase the size of these parts to make, hopefully, at least I can kind of guarantee that the size of these parts large, and these are covers. And if these parts are the only covers of your clutter, then the covering number is high. Okay, so this is a natural way to construct clutters with high covering numbers. Depending on the set of members, these EIs are not necessarily minimum size covers, but still like these are potentially minimal covers. Okay. So if you have all members, all possible combinations of elements, then these are minimal covers. Okay. But the problem is that you have to guarantee that the resulting clutter is ideal. Okay. So taking all members is not possible when you want to keep the idealness. That's the difficult part. So once you impose idealness, it's hard to make the covering number greater than 3, greater than 2. Well, I guess that's the main lesson. Well, anyways, so then how can we kind of construct meaningful classes of ideal clutters from multipartite, this construction of multipartite clutters? What we first looked at is from like binary spaces. Okay, a binary space is a vector space in over Z2. Okay, we are taking 0, 1 vectors that satisfies this equation modulo 2. Okay. For instance, you can look at this 0, 1 hypercube, and this set of 4 vectors is a binary space. So you're taking 0 and 0, 1, 1, 1, 0, 1, and 1, 1, 0. These 4 points, then that will become a binary space. Once you pick this collection of 0, 1 vectors, now you construct a multipartite clutter. And how do you do that? Well, for each coordinate, by the way, we have in the dimension of the space of dimension n, there are n coordinates. But for each coordinate, we construct 2 elements. So the resulting clutter has 2 n elements because 2 elements for each coordinate. Okay. And there are 2 possible values for each coordinate, 0 and 1. And you associate one element with 0 and the other element with 1. Okay. In this example, we have dimension 3. So in the multipartite clutter, we have 6 elements. Okay. And if you have 0, and you take the left one, if the first coordinate has value 1, then you take the second element from this thing. Okay. We have 4 members, 6 elements, but each member has three elements. You don't have to remember this construction, but I guess what I want to say is there's a construction of a multipartite clutter out of this binary space. And we talked about the clutter of triangles in K4, and this is an example of multipartite clutter. Okay? And we proved that the multipartite clutter associated with a binary space is ideal if and only if it has none of these as a minor. Okay, S7 is a clutter of lines in a final plane, and O5 is odd circuits in K5, and B of O5 is the blocker of it. Okay. I mean, the proof relies on the sums of circuits property for binary matrix. There's a nice relationship between binary space, this construction, and binary matrix.
Is it B of O5 is the blocker for the final plane?
Blocker law, not L7, it has to be O. Sorry. Okay, right, but multipartite clutters from binary spaces still has covering number almost 2. So can we generalize this construction for arbitrary fields? So that's what we are doing. So you take any prime power and look at the associated field. Now, instead of taking binary space, we take vector space over GFQ. Okay? And we can generalize this multipartite clutter construction. So for each coordinate, you are getting Q elements. So in the resulting clutter, you have Q times N elements in total. Okay? So it has potentially a covering number of value Q, because each part has Q elements. So we looked at this class of clutters. When Q is odd or 4, then the associated clutter is ideal if and only if it doesn't have a delta 3 as an element. Delta 3 is the edges in a triangle. And when Q is a power of 2 greater than 4, then the clutter is ideal if and only if it has no C5, the edges, the cycle of length 5 as a minor. Okay, so this is for idealness. And for max flow in quad property, we proved the following. This is true for any prime power, not just it can be odd or 2 or 4 or anything. The clutter has max flow in quad property if and only if it doesn't have delta 3 and Q6 as a minor. Okay. So what this theorem implies is that in fact the replication conjecture and the tau equals 2 conjecture are both true for this construction. I guess this is the end of my talk. Thank you.
Thank you very much for the talk. Any questions? So is this a happy ending or sad ending?
Well, I mean, it's happy in the sense that we close this problem, and it's for this class of clutters. But I guess still, like we found that. Well, okay. Getting back to these clutters, like I mean, these are kind of nice examples of non-packing minor. But if you look at the structure of S, it actually turns out to be very restricted. So if you want to have your vector space has this max flow property, it has to be a very restrictive, among the very restrictive class of clutters. So I guess it means that maybe just the vector space is, a multipartite clutter from vector spaces is restricted. So the next question is, can you take arbitrary sets of points as not just a vector space? We can still construct a multipartite clutter. can you understand the idealness or max flow without property? That's the next question. But I'll be happy to continue working on this problem. I guess if anyone among you is interested in kind of looking into more general classes of clutters, then I'd be happy to discuss with you. Yeah.
Do you think this might a similar approach might work if it comes from a projective space that maybe did not come from a vector space?
That's a great question. I guess. Well, okay. I found that so when we looked at vector spaces, we had to use many techniques from matroid and like linear matroid and stuff, just because maybe it's just we are looking at vector spaces. I guess if you are looking at projective spaces, then I guess we could possibly attack this question based on the techniques and tools developed for projective spaces. I guess it would be a interesting question. What I mean, I haven't thought about that, but I find it interesting. Does that answer your question?
Yeah.
Okay.
Is the multipartite clutter minor closed, or?
No.
But if you close it on the minor, then can you find the forbidden minor?
You mean like you take a minor of a multipartite
Yeah.
clutter?
Class of all clutters that are minors or multipartite clutters.
Right. You can actually embed any arbitrary clutter as a minor of a multipartite clutter.
Oh.
So that's actually like, even though this multipartite clutter is restricted, but in fact it's as general as the class of all clutters. It just kind of gives you a different view of looking at this clutter theory, I guess. And again, one advantage of working with this structure is that we can at least try to control the covering number.
And also conversely, if I have a clutter without delta 3 and Q6 as minor, can you say either it's NFMC or blah blah blah? So without saying it's multipartite, can you describe the structure of clutter?
No, it's no. There are kind of much more. There are a lot more like non-ideal and non-packing minors. I mean, like this. I guess this idealness statement. I guess even though we are looking at other like vectors, the fields other than GF2, like delta 3 and C52 are the only forbidden minors. But I guess it seems that the hardest case is when Q equals 2, where we have kind of this seemingly more complex minors. So I'm guessing maybe like this word of GF2 is the most difficult part, I guess. But still here, like we don't understand we don't fully understand the structure other than binary spaces.
One maybe is packing property closed on the taking blocker or
No.
no? Okay.
No.
Ideal was
Idealness is preserved under the taking blockers.
all right. Any questions? So if not, let's speak.